Cauchy-Euler equation. It is this is the general form of it. If you look at it, you would see that each term have x to the power the same number as the order of derivative of that term. For example, this one, y is in the n derivative term, so you have x to the power n times this y. And this y is the derivative of n minus 1. So you have x to the power n minus 1 times with this derivative of y. This one, y is the first derivative, you have x times its term. This one don't have derivative, so you have x to the 0, to the power 0. This is called Euler equation. Now, in order to find the solution of this type of equation, as you see, the coefficient itself is not a constant. Of course, it has a0, a1 until an is a constant, but you have each term you have x to the power something times the derivative of y. So from your previous method, you just can't do the order of reduction because you don't know like what would be the order of your derivative. And the thing is that it's coming as a pattern. There have some basic ways that we can use to solve for the answer of this type of differential equation, which is easier than using the order of reduction method. Okay? So if you have the equation like this, the thing that you have to do is just that assume x is equal to exponential of t. Or from here said that t is equal to ln x. Or dt is equal to 1 over x dx. dt by dx is equal to 1 over x. Okay, here is what is our assumption. And we are going to use this assumption. Okay. Take a look at the first term first, dy by dx. The main technique that we are going to do to find the solution for this type of differential equation is just that we are going to change the x to t. Okay, it's kind of changing parameters from x to t by using this definition. Now, you have dx, dy by dx. I'm going to use the change rule. dy by dx is equal to dy by dt times dt by dx. And you know from our assumption, we've got dt by dx is equal to 1 over x. Okay. Now when we write down dy by dt times dt by dx, it is equal to dt by dx times dy by dx. It's equal, right? Because they have the property of alternate position, right? สลับที่กันคูณนะคะ oh dt sorry and dt by dx is equal to 1 over dt by dx is equal to 1 over x. Okay, so I just put x up there. I would get x dy by dx is equal to dy by dt. You see, x dy by dx is equal to dy by dt. You have the parameter terms in front of dy by dx. But if you use this definition, x is equal to exponential of t, and then you change x to t, you would get that it's equal to dy by dt. Now the coefficient in front of dy by dt is a constant. If it is a constant, then that means you can use our previous method to find the solution of this differential equation, right? Now we can do dy by dx. How about the second derivative of y by dx? Okay, so we do derivative of this term, we would get which is equal to minus, and then dt by dx is equal to 1 over x. So we would get 1 over x squared d square, the second derivative of y by dt, minus 1 over x squared, the first derivative of dy by dt. I take 1 over x squared out, which is equal to I put x squared there to the left hand side. I would get x squared, the second derivative of y by x, on the right hand side. I want to write it down in the term of operator d. Now our d is defined as dy by dt, not by dx, okay? It's turning to by dt, right? So if we do another derivative, I would say it in the term of the general meaning of x to the power n times the n derivative of y by x. It would be equal to d times d minus 1 times until the term of d minus n plus 1y, where our d is equal to dy by dt. Now we are going to use this. So by our definition, we can change the Cauchy-Euler equation in the term of differential equation with the constant coefficient. But don't get that. Remember that the d in this formula means dy by dt. Okay, so that means we got to change the variable by from x to t, and so for the answer, and then change t back to x. That's the way. Okay. Let's take a look at the example. this equation, the Cauchy-Euler equation, you have second derivative of y here, you have x squared here. You have first derivative of y here, you have x here. Is it a Cauchy-Euler? Yes, it is. So if you see the equation like this, you've got to use this assumption. And by this assumption, you would get that x squared equal to c times c minus 1 time until the term of c minus n plus 1. Now our n is equal to 2. Minus 2 plus 1 is equal to minus 1. So that is it. And our term here is equal to, and from this definition we would get c is equal to ln x. Now we are going to put whatever we assume back into our differential equation. So we would get c times d minus 1y plus 3 times cy plus y equal to 1 over 1 plus, can I put x there? I can't, because from the definition here, it means that I already replaced x with exponential of t. So this side there, I cannot put x. I got to put exponential of t instead. Next, after we look at this equation, we have y. Can we put y at the front? We can, because for operator, dy and yd got different meaning. Okay, now each term we have y, so I just take y out. Inside we got d square minus c plus vd plus 1. From this one, if I writing it down in the term of differential equation, I would get this. Now, it is a second order differential equation. It is a non-homogeneous equation. So the answer composed of two parts, which is yc and yp. We are going to find yp first. Oh, I'm sorry, find yc first. Our characteristic equation, m squared plus 2m plus 1 equal to 0. So we got m plus 1 and m plus 1. So m is equal to minus 1 and minus 1. So our yc is equal to c1 plus c2 t, right? It's not x, it's t. Times exponential of minus t. Next, we are going to find yp. Yp, I'm writing y is equal to 1 over pd, which is d squared plus 2d plus 1. times our ft, which is 1 plus what method that we can use to find the answer? Our fs, we can use undetermined coefficient. Can we use shortcut? Can we use shortcut? Can we use shortcut? We can. So what I'm going to do is just I'm going to do the successive integrating. I mean, if you like to do some other techniques else, just do it. But I choose the successive integrating because exponential is not that difficult to do integral.